Hello, everyone. Today we are going to talk about sequences. We are going to start chapter 11. And to talk about sequences, we are going to start with some definitions. So, what is a sequence? Sequence is just a list of numbers. So, like, sequence is, list of numbers in a definite order. Let's look at a couple of lists of numbers. For example, list of numbers. 1, 2, 3, 4, 5. Well, this sequence has 5 terms, and they're just natural numbers from 1 to 5. Another list of numbers. 1, 3, 2, 5, 7, 4. Looks like we have mostly same numbers, but slightly different order of them, right? So we have 1, 3 first, and then 2 even number, and then 2 more odd numbers, and then even number. First, we have more terms in the sequence. Second, the order is different. For sequences, order is going to be important. The first term of a sequence is going to be called A1, or first term. Well, the second term is going to be called A2. I'm going to label this one as A2. And if your sequence has more than 5 or 6 terms, it makes sense to set up a formula for a general term, which is going to be AN. Well, usually we set up formula for general term when our sequence is not limited by 5 numbers or by like finite amount of numbers. Usually we set up a general term when we deal with infinite sequences. For example, we can set a general term as an equals n. And this sequence is going to be defined from n equals 1 to infinity, and it's going to look like this. 1, 2, 3, and it's going to be infinite sequence. Infinite sequence has infinite amount of terms. So actually for every term you have a next one. Okay. We are going to deal in this section mostly with infinite sequences. So sequences which are defined by some general formula or maybe some general rule, and they are always going to have a next term. The one which we have over here is a sequence of natural numbers, right? 1, 2, 3, 4, 5 numbers we use for counting. Well, what other sequences we can have? For example, we can have a sequence looking like this. 1 over 2, 1 over 4, 1 over 8, and so on. You guys probably recognize geometric sequence. General term of this geometric sequence can be described as 1 over 2 to the power of n. We have here 1 over 2 to the power of 1. This one is 1 over 2 to the power of 2, and so on. A general term is going to be 1 over 2 to the power of n. Do we have to start our sequence with n equals 1, like over here? No, guys, we actually can start our sequence with n equals, I don't know, any number actually. I'm going to consider another example, example 2, and let's consider a sequence with a general term n plus 3. So, if we start this sequence from n equals 1 to infinity, terms are going to look like this. A square root of what? We plug in 1 over here. It's going to be square root of 4, and then square root of 5, and then square root of 6, and so on, right? But we also can describe the very same sequence by same formula, but start our, let's say, not by the same formula, by different formula, but start our n with a different number. We can describe it as a square root of n. Over here, we can write down that n equals 4. Let's look how this sequence is going to look. Well, you see that formulas are different, right? And over here, we have a starting n equals 4. So we are going to have our first term as a 4, and then it's going to be 5, and then it's going to be 6. And you see that basically that's a very same sequence. So the formula for the sequence is not unique. Sometimes you can use different formulas. Mostly we are not going to worry about like lots of different formulas for sequences, but you don't have always the same formula. If different people are going to look at the same sequence, they can probably get a different formula for it. Let's try to discover a formula for a sequence from example number 3. I'm going to write down a sequence and we are going to investigate what kind of general formula can create this sequence. So right now I'm going to give you like 4 terms. And I think it's going to be enough to make a statement about a general term. Let's consider sequence, which consists out of 3 over 5, minus 4 over 25, 5 over 125, and minus 6 over 625. So if we want to find a formula, an, what we are going to look? Well, we need to look for some patterns in our like numbers or terms of a sequence, right? If you look at our denominator first, denominator looks like it's powers of 5, right? This is 5 to the power of 1, 5 to the power of 2, here 5 to the power of 3, here 5 to the power of 4. So probably the denominator of my sequence is going to be 5 to the power of n, right? Let's look at numerator. Numerator starts at 3, 4, 5 natural numbers, but they're not going to start with 1. If I have 1 in denominator, how do I get 3 in numerator? Well, I'll need to take this 1 and probably add 2 to it, right? The only one little thing to take care of to make sure that our general term is fitting to the sequence is a minus, right? We see alternation of a minus. How do we describe alternation of a minus in a sequence? Well, because it's a general kind of rule, I'm going to explain it. Let's consider expression minus 1 to the power of n. What kind of sequence we are going to have if we start n from 1? So let's consider just this sequence. Let's see how it's going to work. What kind of terms we are going to have. Let me erase equal sign because term cannot be equal to the whole sequence. So when n equals 1, that's going to be minus 1, right? Sorry, my pen is not working again. Something happens with my pen. I already charged it. Okay, I think it just frozen. Sorry. Let me erase this. So when n equals 1, we are going to have negative 1, right? When n equals 2, that's minus 1 to the power of 2, it's going to be 1. When n equals 3, we're going to have minus 1 to the power of 3, which is going to be negative 1 again. And we are going to have alternation of these minus and plus ones, right? If you look at my sequence, it's not actually similar alternation. I mean, my sequence alternation starts with positive 1, right? So I'm going to consider another sequence as minus 1 and plus 1. What kind of alternation we are going to have here? Well, we've set up n equals 1, we are going to have minus 1 to the power of 2. And then minus 1 to the power of 3, minus 1 to the power of 4, and so on. You see that there are 2 different ways to alternate the sign, starting with minus or starting with plus. You can describe this alternation by minus 1 either to the power of n or to the power of n plus 1. usually it's going to depend on what is your original one. In our case, because alternation is starting with positive 1, we are going to have minus 1 to the power of n plus 1. Okay, and that's going to be general formula for my sequence. Very nice. Let's consider some unusual sequences. Not always a sequence is going to be given by a formula. Sometimes a sequence is going to be given by connection between the terms. Let's consider so-called Fibonacci sequence. Sorry, it's supposed to be 2 B's. Or 1B, yeah, 1B and 2 C's. Fibonacci sequence. Fibonacci sequence is given recursively. How it works? We are going to set up the first term, A1, and you're going to say A1 equals 1. Then going to set up A2 and say that A2 also equals 1. And then you are going to set up formula for term n. And that's going to consist out of term n minus 2 plus term n minus 1. So the next term is made out of the sum of 2 previous terms. Let's see how the numbers of this Fibonacci sequence are going to look. The first term is 1. The second term is 1. And the third term is 1 plus 1, which is going to be 2, right? And the fourth term, 1 plus 2 is 3, and 2 plus 3 is 5, and 3 plus 5 is 8, and 8 plus 5 is 13, and so on. So here, guys, we can not predict term number n by just using a regular formula, because actually term number n depends on term numbers n minus 1 and minus 2, and they depend in their turn in the all previous terms. So Fibonacci sequence is not that simple. This is just example of like a sequence. Now, well, guys, let's consider a sequence which is going to be something like let's say sequence 1 over n. Sorry, pressed something wrong. My next example 5. I'm going to consider a sequence 1 over n. How this sequence is going to look? 1n equals 1 is going to be 1, right? N equals 2 is 1 over 2, and then it's 1 over 3, and then it's 1 over 4, and so on. How can I graph terms of this sequence? There are 2 ways to graph them. First, I can use number line and kind of have over here 0, and I'm going to have over here 1. You'll probably ask me, why do I have that 1 that far away? Well, I'm having 1 that far away because all my terms are less than 1 or like equal to 1. Now, I'm going to graph my first term. My first term is sitting over here, 1. My second term is 1/2. My third term is 1 over 3, approximately here. Then 1 over 4 over here. Then 1 over 5 over here. 1 over 6. And guys, you see that term starts concentrating around number 0. They are not going to become 0 ever, because no matter which n you plug in denominator, it's still going to be some positive number, right? But they're going to be very close, like having lots of actual terms around 0. So 0 looks like a special point for this sequence, right? And I'm going to describe a second way to draw the sequence. We can treat a sequence as a function of n, f of n. Imagine that you have a function of imagine that we have a function f of x, which is 1 over x. And then we are going to plug in, instead of x, only natural numbers, like 1, 2, 3. So we are going to have 1 over n. If we consider like numbers 1 over here, 2 here, 3 here, or like they are my axis, and the value is going to be f of x. So I'm going to have a set of points looking like this. 1, 1. The next point is going to be 2, 1 over 2, 3, 1 over 3. Let's graph these points. So let's imagine that over here we have y and over here we have 1. So my first point is 1, 1 sitting over here. My second point is 2, 1 half. My third point is 3, 1 over 3, and so on. So these points are going to actually sit on the function 1 over x, like little kind of beds sitting on the string like this. They're going to just like certain points. So guys, what do we see from these two pictures? We see the points are coming closer and closer to a certain number. And we know from like theory of functions, when function is coming closer and closer to a certain number, it's going to make up a limit. And the sequence, which is going to have a limit or concentrate nearby a certain number, is going to be called convergent sequence. So I'm going to set up a precise definition of a limit, but from the picture, it's going to be something like this. When points start concentrating around a certain number. Here, for example, they concentrate around 0. They're very dense around 0, and you can get very close to 0 by just changing your denominator further away, right? So there is going to be precise definition of a limit. We're not going to use it a lot, but you're supposed to know it. Precise definition of a limit. Definition. A sequence an has a limit L, and we write it like this: limit of an as n approaches infinity equals L if for every epsilon greater than 0 exists big number n integer such that for any n greater than n, we are going to have that an minus limit is less than epsilon. You probably are going to look at this definition and recall definition of a limit of a function. Remember, delta epsilon definition of a limit of a function. So here, guys, we don't have delta because like our x is not actually a real number. We have n as a natural number or positive integer number, which is going to go to infinity. N is becoming bigger and bigger and bigger. What this definition tells us? That for every number epsilon, no matter how small it is, if we claim that number L is a limit, in this case, for example, we claim that actually 0 is a limit, right? I'm going to kind of graph this. 0 is a limit. We are claiming that L equals 0 in this case, right? The definition tells that for any number epsilon, no matter how small it is, number epsilon, usually it's a number to which the limit is different from a term of a function. You see, when you have inequality like this, means that the difference or distance between limit and the term is less than epsilon. If you choose epsilon like this, then you can make n terms big enough, starting with certain number, that all terms are going to get within like this distance. Like over here, for example. Well, I don't know like what is my epsilon, but I think it's a little bit less than 1/2. And if I choose any number starting with number 3 over here, if I choose my big N 3, starting with n equals 3, even with n equals 2, all the terms are going to be between like this 1/2 and my limit, which is equal to 0. Let me show you how it going to work, like, because precise definition of a limit sometimes can be kind of difficult to understand. And in this sequence, we are going to say that an, the sequence an is convergent. If the sequence does not have a number or limit L, it's going to be called divergence. Divergent. Let me write it down. Definition. If there is no L as a limit, an is divergent. First, I'm going to consider a convergent sequence, and I'll try to figure out like how do we consider like how to find this big N and everything. So guys, I'm going to consider a kind of book example sequence, which is going to be like, let's consider example number 6, I guess. And my sequence is going to be n plus 1. So we take major. How the terms of the sequence are going to look? They are going to look like if n is equal 1, it's 1 over 2, right? N equals 2, it's 2 over 3, 3 over 4, 4 over 5, and so on. Okay, so, well, first, let's figure out what is a limit. I'm going to just try to do it mathematically. n plus 1, n goes to infinity. I'm going to do here, guys. I'm going to divide by n, numerator and denominator. I'm going to get numerator is 1, here is 1, and here is 1 over n, right? What is going to happen to 1 over n? When n goes to infinity, it will go to 0. So I expect limit equals to 1. Now, what I'll need to show? I'll need to show that using definition, using definition, that for any epsilon greater than 0, exists big N such that for n greater than big N, 1, not 1, sorry, n over n plus 1 minus my actual limit is L, is going to be less than this epsilon. Well, guys, if you remember how we were doing it with functions, actually, epsilon is something which is going to be given to us, and it can be a big or a small number. Our goal is to show that we will be able to provide big N, starting with which all terms are going to be close enough to our limit. So we can provide it. We'll need to, basically, the idea is to find N, which is going to be N of epsilon, of course. Usually we prefer to have a formula, right? How are we going to do it? Well, we are going to just kind of work with this. Remember, we have some kind of backward work. We are going to work with this inequality and eventually get to this inequality. So let me kind of have it. I'm going to bring everything to common denominator. And common denominator is going to give me what? N minus n, here minus 1, right? So I'm going to have actually what? Minus 1 over n plus 1, absolute value is supposed to be less than epsilon, which is going to bring me to minus 1 absolute value is equal to 1. 1 over n plus 1 is supposed to be less than epsilon. And I'm going to modify it a little bit. I'm going to multiply by n plus 1 on both sides. And divide by epsilon on both sides. So here we cancel this, here we cancel this. We have 1 over epsilon less than n plus 1, or 1 over epsilon minus 1 less than n. If you compare this expression to what we need, we'll need to figure out for which big N little n is going to satisfy all these conditions back over here. So if we choose big N, let's say greater than this number, we can choose big N equals to this number. I'm trying to say what, if we choose big N equals to this number, we are going to have something like this. Big N and little n is greater than big N. Only thing is that this number is not necessary, is going to be a natural number or integer. We'll need to figure out like a first natural number or integer, which is going to be like bigger than this. So, well, I don't know. I'm going to just choose some epsilon to show you how it works. Again, we're not going to prove lots of stuff by definition, but to understand the idea of this convergence, we will need to know how everything is working. So I'm going to consider, like, let's imagine somebody gives us epsilon equals 0.1, and they're asking, what is n from which we can from which inequality n over n plus 1 minus 1 is going to be less than 0.1? Starting with which n that's going to be true for any little n. Well, according to my formula, big N is like the first natural number. I'm going to just plug everything into my formula. So 1 over epsilon is going to be 1 over 0.1 minus 1, which is going to give you what? 10 minus 1, which is going to give me 9. Well, guys, because my choice of epsilon was 0.1, my number is actually like a natural number. But you should understand that it's not always going to be the truth. Somebody is going to give you something like 1.9 here, and that's going to be some number with decimal digits. You will need to find a kind of natural number, which is going to like a little bit bigger than the one which formula gives you. So actually, from where we can say that for all little n which are greater than 9, this inequality is going to be true. Well, let's check it for n equals 10. For example, this is going to work for n equals 10, which is greater than 9. Let's check. 10 over 10 plus 1 minus 1. Is it going to be less than 0.1? What we have over here. 10 over 11 minus 1 less than 0.1. I'll need to develop it a little bit to show you literally that it's going to work. So we have 10 minus 11 over 11, 0.1. And what I have, minus 1 here, absolute value is going to change it. It's 1 over 11 less than, what is this? This is 0.1, which is 1 over 10. Do you see that this statement is true because it's just like 1 over 11 is less than 1 over 10. So you see, so all numbers n greater than 9 are going to satisfy this inequality. Well, this is formality, but some theorems are hard to prove without having a formal base. So how the sequence can converge? Let me show you several different ways for the sequence to converge to a certain number. Again, they're going to be hypothetical cases. Let me move it up. And how the sequence is going to diverge. Convergent. I'm not going to give you the formula. I'm just going to show you pictures of convergent sequences, okay? And over here, I'm going to put divergent. Later, we already considered a couple of convergent sequences, right? I'm going to give you a couple of divergent sequences also. Let's imagine that limit is over here. So that's my L, that's my limit. How the sequence can be convergent to this limit? Remember that we do graph the sequence at just points like 1, 2, 3, just natural numbers. So, well, we can do something like this, for example. So, sequence can converge like this, or sequence can converge like that. 1, then 2, 3. Get closer and closer to a, or I'm trying to get a different color. Sequence can converge like this. It's not very important how points are concentrating around the limit. On the, like from the top, from the bottom, or from both sides. It's important that they are concentrating. And you are going to see what I mean when I draw divergent sequences. My first divergent is going to look like this. Let me label 1, 2, 3, 4, 5. For example, you have number here, 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 number here. You see that these green points are not concentrating around the same number. Some of them are concentrating around here, some of them are concentrating around here, but they're not concentrating around the same number. So this sequence is divergent. And it has no limit. Another divergent sequence can look like this. Mm, 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 mm. Something like that can go to infinity. When sequence goes to infinity, it's also divergent, but we are going to specifically tell which way it is divergent. We are going to say that it equals to infinity. Again, we don't mean that actually infinity is a number by this. We just mean that, well, that sequence is not doing this up and down jumping or random jumping everywhere. Like we can have sequences which are not even doing this pattern. They just jump like around all numbers. But sequence kind of steadily goes to infinity or negative infinity. And so these are like basic things about limits. I'm not going to give you precise definition of infinite limit because again, we are not going to prove nothing by definition. Mostly we are going to use limit laws. We are going to now describe some limit laws and kind of work with convergent sequences. We're going to start with the first theorem. I'm going to label it as theorem 1. Okay, you can kind of give it a different name or whatever. Well, guys, the theorem is going to sound next. If limit of a function f of x as x approaches infinity equals L, then limit of a sequence f of n as n approaches infinity is going to be equal to the very same number L. Well, why does it happen? Well, a little illustration. So, well, I don't know like how the function is approaching L, but let's imagine that this is my L and the function is doing something like this. Function is approaching the limit at infinity. Basically, we remember that this means a horizontal asymptote, right? Now, the sequence is going to make up only points on this function, right? But because these points or dots are sitting on the function, they will follow the function. That's just like a rail, which is going to bring the points to the same number as like function goes. So the theorem is very good because we know lots of stuff about limits of functions, right? For example, L'Hopital's rule, a good rule to use against functions. We can apply them to sequences. We cannot apply L'Hopital's rule, for example, directly to sequences because we cannot differentiate sequences. Sequences, because they depend on natural numbers or like positive integers, we cannot differentiate them because they kind of, you cannot set up derivative for a sequence. But if you go to functions and find the limit for functions, then you can say that limit of a sequence is going to be the same. I'm going to consider something like limit more like limit laws and then give you a couple of examples. Okay, go back. Limit laws are same for sequences as for functions. So if you have two sequences and you add them or subtract them, and you do have limits separately of an and bn, then the limit, like for functions, is going to be equal to the sum of limit or to the difference of limit. Number two, limit of a product. Again, in case you do have both lists, of course, it's not just like, if one of them do not have limit, it's going to be a different story then. It's limit of an by limit of bs. Number three, for quotients a and bn. Again, considering that both have limits and limit of bn is not equal to 0. Yeah, guys, already cannot squeeze over here and goes to infinity, but trust me, that's supposed to be. And number four, we can separate as a kind of separate law. If you multiply your sequence by a constant number, for example, take a sequence and multiply it by 2. For a limit, it's not important. You can always take this constant number outside of the limit and just calculate the limit of a sequence. Number five, a limit of an to some power of p, where power of p is greater than 0 and terms are greater than 0. Positively termed sequence in a positive power p, constant power, squaring. Imagine that you have a sequence and you decided to square every term of that sequence. Then, guys, you can find the limit of that sequence and then square it, and that's going to be the limit of that squared sequence. I'm going to use it sometimes. You'll see how it works. And number 6, I'm almost done with theorems. Number 6 is going to be squeeze theorem. Squeeze theorem is going to deal with a set of 3 sequences. Sequence an, which is less than sequence bn, and which is less than sequence cn. And it's not necessary that they're supposed to work for all numbers n. Just starting with certain number n, this inequality is true. And if you know that limit of an equals L and equals to limit of Cn. So if outer sequences have the same limit, then limit of Bn, the one which is in between, that's why we call it squeeze theorem, is also equal to L. Well, if sequence is sitting between two convergent sequences, it's going to converge and the limit is going to be equal to the same number. There is no escape for that sequence, right? Okay, so, no, I said that's the last theorem, but actually not the last theorem. Actually, there one more. And this theorem is dealing with absolute value limits. If limit of set of absolute values over certain sequence is equal to 0, then limit of terms by themselves is going to be equal to 0 too. Well, for example, you have a sequence which is kind of having alternating terms, positive, negative, positive, negative, positive, negative. Imagine that you kind of don't know where it goes. Drop the minus and see where goes absolute values. If absolute values go to 0, then the original sequence will go to 0. And I'm going to consider example for like maybe each of these 7 laws plus theorem number 1, which is going to be just maybe law number 0. Okay, just give me a second. Okay, guys, I want to consider several examples, and I want to put my examples kind of next to the theorem I want to illustrate. Let's consider the sequence an, which looks like a ln of n over n, and try to find what is the limit of this sequence. Limit of an is a question. So, well, we have seen this, right, when we were doing L'Hopital's rule. But again, I told you that L'Hopital's rule is involving differentiation. We don't know what is derivative of n because n is a natural number. So we're not going to actually differentiate a sequence. We are going to create a function f of x, which is going to be similar to a sequence just using real numbers instead of positive integers. And try to figure out limit. What is going to be the limit as x approaches infinity of ln of x over x. My goal is to use the theorem over here. If function has a certain limit, then the sequence is going to have the same limit. Well, what we have over here, guys, when x approaches infinity, what we have? We have infinity as ln and infinity as x, means that we can use L'Hopital's rule, right? Let me kind of use L'Hopital's rule. L'Hopital's rule tells us differentiate numerator, differentiate denominator. ln is going to give us 1 over x is going to give us 1. And basically, guys, we are going to have a limit of 1 over x approaches infinity. And we do know that it's going to be equal to 0. Now, using theorem 1, we can say that limit of ln of n over n as n approaches infinity also equals to 0 by theorem 1. Okay, guys, I know that formally differentiation of ln of n over n and ln of x over x is going to look same. But again, usually it kind of brings to a question, does the student understand that he cannot differentiate natural numbers or like integers? So do this substitution with x and differentiate x, just to show that you kind of know the rules. Okay? Okay, very good. So we did this example. Now, I'm going to jump to the last one. I'm going to do the between ones too, but for the last one, I'm going to put. For the last one, I'm going to consider a sequence an, which is going to be -1 to the power of n over n. And I'm going to look for the limit of an as n approaches infinity. Question. Well, because I'm planning to use this theorem numbers, like a property number 7 or theorem, which is coming like under number 7. I'm going to calculate a limit of absolute value of ln, an. And absolute value of this number is going to be what? -1 to the power of n over n. If I take absolute value, -1 disappears, and that's going to be limit of 1 over n, right? N goes to infinity. And so limit of 1n goes to infinity, 1 over n goes to 0, right? And which means that if absolute value goes to 0, then original limit is going to be equal to 0. Okay. Says maybe we can use our squeeze theorem. It's not going to be enough space next to squeeze theorem to place my use of it, so I'm going to put squeeze theorem separately. Example, use squeeze theorem. Let's consider a sequence which is going to look like this. An equals n factorial over n to the power of n. For people who forgot what is factorial. For example, 3 factorial, it's a product of 1 by 2 by 3. So n factorial is a product for all numbers starting with n and ending with 1. So how my terms of a sequence are going to look? When n equals 1, it's 1 divided over 1, right? N equals 2, it's 1 multiplied by 2, and n in denominator is 2 by to the power of 2, 2 by 2. 1 by 2 by 3, 3 by 3 by 3. 1 by 2 by 3 by 4 is 4, 4, 4, 4, and some other terms, right? Well, guys, what do we see? Let's look at term number 4. We see that in term number 4, this 4 is going to kind of cancel, right? These two fractions are less than 1, okay, right? And this is just 1 over 4. This equals 1 over 4. So we can say that the whole term is less than 1 over 4. Why? Well, because if you take 1 over 4 multiplied by something less than 1, you are going to get a number less than 1 over 4. This term, same way, is going to be less than 1 over 3. This term is not going to be less than 1 over 2 because there is nothing which is like 2 over 3, which is making it less, but it's going to be equals 1 over 2. And this term equals 1. Why I'm doing this? I'll need to build two sequences. Consider that this is my inner sequence. I'll need to have like sequence Bn, which is less than and sequence Cn, which is greater, right? What I'm trying to do right now, I'm trying to figure out what is a sequence which is greater than all the terms. It looks like the sequence which is greater is going to be 1 over n. Like, for example, for term number 4, it's 1 over 4, 1 over 3, 1 over 2, 1. And it's allowed to have equal sign. Sorry, I have a call to, yes. Okay, what is going to be my other one? The sequence on the bottom. Well, guys, can be actually lots of different sequences which are just less than this one. For example, a sequence of negative ones. Imagine that you take a bunch of negative ones and they are all going to be less than terms of this one. When you choose the bottom one, you will need to kind of think about like ahead, what kind of limit you are trying to prove. What is going to happen over here, guys? What is the limit of this one? We already know that limit of 1 over n is going to 0. So we need some sequence in the bottom which will have like 0 as a limit. And a very good sequence actually is going to be just a 0 sequence, looking like this. 0, 0, 0, 0. This sequence is less than all like terms over here, right? And on the other end, a sequence of 0 is going to have a limit as 0 because it's just a constant. So what we see, the limit of Bn equals 0 equals the limit of Cn, which is 1 over n also, right? And we do have that we squeezed our sequence between 0 and 1 over n. I'm going to write down 0. I'm going to write down less or equal n factorial over n to the power of n, less or equal than 1 over n. And the limit of this one is 0. The limit of this one is 0. So the limit of this one is going to be 0 too. Yeah, so we did the squeeze. We use the squeeze theorem and the limit is going to be equal to 0. Very good. So we just have one more sequence to consider. And that's going to be one of very good sequences which we are planning to use in future. So let me do that. And the first part of our lecture is going to be over. I'm going to go back to my purple color and give me a second and consider a special sequence, which is going to look like this. A sequence of r to the power of n. Well, what is r? R is going to be any real number. N is just a natural number. You can consider it starting with 0 or starting with 1, depending on like what you like. And we want to investigate how this sequence behaves depending on R? Like, what do we have depending on R? I'm going to start with considering different R's. First, let's consider R equals 1. In case R equals 1, let me label it as case number 1. We have a sequence of 1, 1, 1, and 1. Looks like no sequence at all, just a bunch of ones. We know that limit of such sequence is going to be equals to 1, right? As n goes to infinity. So this sequence is convergent, converges to 1. Not very interesting, but convergent. Case number 2, let's consider R equals 0. Bunch of zeros, and the limit is going to be n goes to infinity equals to 0, right? So I'm trying to use numbers, special points, let's say, and then I'm going to consider what happens in between, okay? Yeah, maybe I'm going to consider maybe -1, makes sense to consider first points. R equals -1. When R equals -1, we have -1 to the 1 and -1 to the power of 2, and then -1, and then again. So, well, remember we had a special sequence which had no limit because it was oscillating -1 plus 1 -1 plus 1, did not go to any number. Limit does not exist, divergent. Okay, so what happens in between these numbers? Let's investigate. Let's investigate. So guys, let's now consider cases in between. I'm going to draw actually number line and label the points. The 0.1 -1. So at 0 it converges to 0, at 1 it converges to 1, at -1 divergent. Now let's consider this interval r greater than 1. R greater than 1, function f of x is going to be r to the power of x. And r greater than 1, looks like we are going to have exponential functions. Okay, like this, right? Base greater than 1, increasing exponential function. So what do we have? Well, the function goes to infinity and means that over here, the limit is infinity, which is also divergent. What is going to happen between 0 and 1? Between 0 and 1, I'm going to write down r less than 1, greater than 0. Well, again, the same function, f of x equals r to the power of x. I'm trying to use that the fact. When r is less than 1, the graph we have, it's a decreasing exponential function looking like this, right? And the limit is going to be equal to 0. So I'm going to say that limit over here is equal to 0. I'm going to draw 0 over here, but kind of see it over here. Well, we know what happens at 0. Now, what is going to happen between -1 and 0? What if r is less than 0 but greater than -1? Well, guys, we cannot describe the result by one function. I'm going to write down like how the, the sequence is going to look. So it's going to look if it's a negative number, when you raise it to different powers, it's going to be alternation of a sign, plus minus, plus minus, plus minus. So the first one is going to be like minus r, the second one is going to be r square and minus r cube and so on. Well, it looks like this case is going to be lost for the limit, but if you draw the picture as all negative exponents are going to go like this, and all positive exponents are going to go like this. Like negative numbers are going to sit here, here, and here. Positive numbers are going to sit here, here, and here. So it's kind of r to the power of x and minus r to the power of x. We see that the sequence is still going to approach 0, just not like from the bottom or from the top. So limit here is also 0. Only one last we are going to consider is last area when the r is less than -1. We are going to have f of x. Well, it's again not one f of x. I'm going to draw like two actually. So terms are going to be very similar to this one. So it's going to be minus r squared, minus r cubed, r to the power of 4, and so on. If I graph these numbers, I'm going to get something like, because r is going to be by absolute value, r is greater than 1. They are going to be two exponential functions which increase. These ones are going to go over here, and over here, right? Negative ones are going to sit in between. This function, if you consider this sequence, it's not even having a limit infinity. It has absolutely no limit because some of the points going to positive infinity, some go to negative infinity. So I'm going to write down does not exist over here. Limit does not exist. Does not exist. So guys, if we go back to our original picture, we're going to see that the good points where the sequence is convergent are going to be from here to here. I'm going to describe them. So limit of r to the power of n goes to infinity is going to be equal to what? Well, 0 when r by absolute value is less than 1. I'm trying to describe this interval. 0 here, 0 here, 0 here. And that's going to be equal to 1 when r is equal to 1. And this is going to be only two convergent cases, the one inside of the interval and the endpoint. This endpoint is divergent. We already know no limit. This part is divergent because it doesn't go anywhere positive or negative infinity, and this part is divergent because it goes to positive infinity. We'll need to kind of remember about this sequence. I'll give you maybe a couple of examples to see how it works. So let's consider example number 1. Let's consider what is going to be the limit 3 to the power of n. Well, 3 to the power of n is greater than 1, so belongs to this area, so limit is going to be infinity. And you don't need to calculate it actually over, because it's already known that it's going to be infinity. What is going to be the limit of -1 over 3 to the power of n? N goes to infinity. Where is r? This is r. My r equals -1 over 3. My pen is kind of dying. Okay, -1 over 3 sits over here somewhere. -1 over 3. And it's within the interval which brings me to 0. So the limit is going to be equal to 0. You now, guys, can use this theorem and just state the limits without actually considering how the limit is like calculated, because we kind of proved it already. Okay, now guys, we are going to stop at this point. There is about half of the section left, which I'm going to teach in next lecture, okay? And I'm going to also kind of assign problems next lecture. My suggestion, guys, if you did not get this special sequence, go over it from your book, because maybe I was too fast.